Welcome back to ECE 320. In this video, I want to try to share a big picture view of the Laplace transform. We're still in Unit 4, still learning the basics of the Laplace transform and trying to become a little bit more comfortable with it. But I want to indicate or provide a little bit of insight into where this can lead us or why we are spending so much time trying to understand the Laplace transform. And the reason is that it has a lot of application. We can use the Laplace transform to produce transfer functions. We can start talking about poles and zeros. We'll start understanding a little bit better where this Bode plot might be coming from and how it's connected to the transfer function. And once we have the Bode plots or these frequency responses, now if we start sketching those, can we actually design filters based on a desired shape or frequency response behavior or Bode plot that we now have envisioned or need to achieve a particular behavior in a system that we might be wanting to design or create. This big picture view of Laplace transforms, again, I want you to be thinking about moving back and forth between two different locations. We're playing with two different domains. We're in the time domain sometimes, we're in the frequency domain some other times, and we want to get very comfortable moving back and forth and making the connection between these two different ways of thinking. The time domain is f of t, the frequency domain is capital F of s, and they're connected by the Laplace transform, and we're using the one-sided Laplace transform, which means that we're worrying about the functional value f of t over a support interval from 0 minus up to infinity. The Laplace transform then looks at that time domain waveform for all time from 0 minus to infinity. It scales it or weights it with this complex exponential e to the minus st. It combines those as a function of time and integrates those two waveforms together to produce a transformed expression or quantity, capital F of s, and we want to now understand how all of that time domain information is condensed or compacted down into or preserved in this frequency domain expression, capital F of s. In this class, we're going to concentrate on circuit analysis via or using the Laplace transform, but as we end this short video, I'll indicate that you can actually apply the Laplace transform in many other areas besides or beyond or outside of circuit analysis. For our purposes, we will focus on transfer functions. Here's a transfer function, which is really a model of some system. And in this case, you could think of it as a low-pass filter. It has a ratio of polynomials of s, the numerator polynomial, which will produce the zeros, and we'll then talk about poles and zeros. The numerator polynomial, or the finite values of s that cause the numerator to vanish, will be called the zeros. Those are the open circuits in our pole zero diagram. The values of s that cause the denominator to vanish are the values of s that cause h of s to go unbounded, which are called poles. And you can think of this now as a circus tent, where you maybe have this circus canopy is a elastic sheet, and underneath that elastic sheet you erect infinitely tall poles at the pole locations, and that produces this surface on top of the complex plane, and that surface now provides us with some insight into the magnitude of the frequency behavior at different locations in the complex plane. And we will typically be walking underneath that circus tent along the imaginary axis, and that provides us with the frequency response information that we want. So it's very important to understand these transfer functions and how we can create those from a circuit in this class, how we can now connect those transfer functions or talk about those transfer functions in terms of poles and zeros. We can then use those transfer functions to create Bode plots, which not only will we worry about the magnitude response, that's what the vertical lines mean. We're taking the magnitude of h evaluated at s equal j omega, and j omega is the imaginary axis in the complex plane. We want to walk along that imaginary axis. We're walking at different values of omega, and as we walk along that imaginary axis, we're looking up at the circus tent and trying to find out how high or where that particular level of the surface tent is, and we could think of that then as this magnitude response or Bode plot as a function of omega. We start at we start at a frequency that's very, very small. In a Bode plot, our horizontal axis is logarithmic, so we never really get, if we were to keep walking to the left on this Bode plot on the horizontal axis, we would never get to where we were wanting to start, which is maybe DC or a low frequency. We would just keep going to 0 0.1, 0.01, 0.001. It's a logarithmic axis, so we would never get to zero, but we would get to smaller and smaller values of omega. Contrast that with the complex S-plane that we usually represent in a finite plane. There we can start at the origin, that's zero, and we can walk up the positive imaginary axis and take on different values of omega. The circus tent is now superimposed or put on top of this complex S-plane with poles, infinitely tall poles located where the x's are. In this particular Bode plot, we now have a pole at omega equal to 10, or J10 in the complex S-plane. We would have a circus tent in magnitude that is relatively flat until we hit that pole, and then it would start, the circus tent height would start approaching the ground, and the the vertical scale is also in dB, and so we would really never get to the ground. We would just keep going down and down, and we slope. If we had a single pole, we would be sloping at 20 dB per decade down from that pole location at omega equal to 10. And we will get a little bit more comfortable with the slopes, but a decade now is a factor of 10, which means that if we start decreasing in magnitude at omega equal to 10, and this is a straight line approximation, it's not quite what the exact magnitude response looks like, but we will concentrate on these straight line approximations for the Bode plot. At omega equal 10, let's say that we start at 0 dB, then 20 dB per decade. A decade beyond 10 is a factor of 10, which means that 10 times 10, or if we were to move out to omega equal to 100 in this Bode plot and look at the magnitude of our transfer function at 100, it would be at minus 20 dB. If we go another decade, which is a factor of 10 beyond 100, now we are at omega equal to 1,000. We would be 20 dB down from where we were, and we were at minus 20 dB. Now we're 20 dB beyond that, so we're now at minus 40 dB at 1,000. And you can see then that how this magnitude response rolls off as a function of frequency. We can generalize that. That was a low-pass filter. We're passing low frequencies. We're not favoring higher frequencies, or we're attenuating frequencies that are higher than omega equal to 10. That's a low-pass behavior or characteristic. We could do just the reverse and say, let's favor high frequencies and attenuate frequencies that are low. Then we would have a filter or a magnitude response that's increasing as we get higher in frequency, and then it levels off after a given frequency. That would be a high pass. We could favor particular frequencies in a band. So we might discard low frequencies, we might discard high frequencies, and we might favor a particular band of frequencies. Or we could do the reverse of that, and we could reject frequencies in a particular band. And depending on how we want to shape this band reject, we might have something that's fairly flat at low frequencies and high frequencies, and then it throws away or tries to discard frequencies in this intermediate band between two other frequencies that might be indicated by these limits on our particular band reject filter. These are very powerful concepts, and as I said, we can apply those in many different domains, not just electric circuits, but we could do it in all of electrical type environments. We could do it in mechanical, electromechanical, think motors or generators, thermal. Now you have maybe some temperature environment, chemical, optical. We could be processing all of these using these concepts of the Laplace transform. And finally, let's now connect the time domain with the frequency domain. The time domain, there we have an impulse response. If we excited the system with an impulse function, then what we see at the output after exciting the system with an impulse at the source would be our impulse response. That's this little h of t. That's how the circuit behaves for an impulse function. We can use that in the convolution integral to determine what the output would be for a generic input x of t, not just the impulse. If x of t were the impulse, then the output y of t would be the impulse response because of the way the impulse function sifts out what's inside the integral. That's what happens in the time domain. We find the impulse response, or we use the impulse response of our system. We convolve that with the input x of t, and that produces the output. The reason why we might want to move back and forth between the time domain and the frequency domain is if we transform all of these time domain signals and systems, x of t and y of t would be signals. We transform those into the frequency domain. We could transform the system's impulse response into the frequency domain to find the transfer function h of s. That now we could find the output if we were given the input x and the system's transfer function capital H of s. We could produce the transform of the output by multiplication, and we wouldn't have to do this time domain convolution. Once we had this frequency domain version of our output in the form of this transform capital Y of s, we could then go back into the time domain by inverse Laplace transforming, and we'll have to worry about that concept later, but we will learn how to go now from the frequency domain back into the time domain, and that will be using the inverse Laplace transform. But this is now a big picture view of the Laplace transform. It will take us many different places, but we want to become very comfortable with making these or computing these Laplace transforms because they will provide us or allow us to think more generally in terms of what's happening. We can now think about frequency response, Bode plots, filters, poles and zeros, and transfer functions, all by this concept of the Laplace transform, and that will open up a lot of opportunity for our understanding of electrical systems.